Workshop talk and our weekly Simon Center talk. And we're pleased to have Gabor Szekelyhidi from Notre Dame, who will talk about extremal metrics on toric manifolds.
Well, thank you very much for the opportunity to talk here. So I also realized that my talk will most likely be a little bit too elementary for most people here, but I hope it will still be interesting. Okay, so let me just give a sort of brief outline of what I want to talk about. So first I'll talk about extremal Kähler metrics in general. And then I will specialize to like toric manifolds. So I will give a very brief introduction to Kähler geometry on toric manifolds, and then I want to sort of explain what this Yau-Tian and Donaldson conjecture is. So at least I want to make a precise statement in the case of toric manifolds. And then finally, I want to very briefly just say what's known at present. So what are the existence results? Okay, so this is the kind of outline for the talk. Okay, so for extremal Kähler metrics, well, these go back to Calabi in the 80s. And he was interested in finding like canonical Kähler metrics on Kähler manifolds. So if we pick a Kähler manifold, say M omega, and let's say the dimension is n throughout this talk, then Calabi introduced this notion of extremal metric, which was a metric in the same Kähler class as big omega. If it is a critical point of this so-called Calabi functional. So let me write this cal omega. And this is the scalar curvature squared, the integral of the scalar curvature squared with respect to the volume form given by omega. So you want the critical point of this over the Kähler class. So it's sort of very analogous to like the Yang-Mills functional in the study of like vector bundles. Okay, so then of course you can do a calculation, which is, I mean, it's not trivial, but I think Calabi is very good at these things. So the Euler-Lagrange equation. I mean, of course, you can certainly calculate it, but then it turns out that it has a very interesting geometric interpretation. And what it says is just that the gradient of the scalar curvature it preserves the complex structure. So it is the holomorphic vector field. And then, of course, there are some very special cases. Well, first, I suppose most compact Kähler manifolds do not have any non-zero holomorphic vector fields, and in that case, this would mean that the scalar curvature is constant. So this is the usually abbreviated CSCK.
So the Euler-Lagrange equation is that vector field is holomorphic?
Yep. I guess d bar. Okay, d bar of this is 0. Yeah, so omega is extremal if this is holomorphic. And then an even more special case is when the Ricci curvature is constant. So these these are the Kahler-Einstein metrics. And then one thing that I don't want to say much about at all, but it sort of, I think, permeates a lot of the theory, is that the scalar curvature, so this is due to Fujiki, and then rediscovered by Donaldson. And there are like precursors to it by Cullen, Atiyah, Bosch. So this is really a kind of key thing to keep in mind. It's the fact that the scalar curvature arises as a moment map. But I don't want to spend too much time on making this precise, but I will just say one thing about it a little bit later. So it arises as a moment map for an infinite dimensional action, namely the action of the symplectomorphism group of this. You just treat this as a symplectic manifold, and then you let this act on all the complex structures compatible with omega. So and in particular, this point of view that in Kähler geometry, traditionally, you want to fix a complex structure and vary the Kähler form. To change this point of view to this picture where you sort of fix the symplectic form, but then vary the complex structure, this is kind of an important feature in various works on extremal metrics. And it's quite important in the toric case, too. OK, so well, I mean, I definitely don't have time to survey all results on extremal metrics, but one very important one, which again sort of relies heavily on this like heuristic sort of infinite dimensional picture, is that extremal metrics are unique whenever they exist. So up to the action of the automorphism group of the manifold. So in various degrees of generality, this goes back to Bando Mabuchi. In the Kähler-Einstein case, and then there are stronger results by Donaldson, Chen, Tian, and Berman, Bernsen. So this uniqueness question is very well understood by now. So of course, the key question is the existence. And then roughly speaking, well, I can state this precisely, but I won't define the words yet. So this Yao-Tian-Donaldson conjecture is that is a characterization of when you can have an extremal metric. Okay, so it doesn't apply to arbitrary Kähler manifolds, but rather to get a link with algebraic geometry, you only take the ones where the Kähler class is the first term class of a line bundle. So we assume that you have a positive line bundle, and that's the Kähler class that you're working with. And then in this case, M admits. So let me state it for CSCK metrics. The conjecture is that M admits a CSCK metric in this class if and only if the pair, so this projective variety, is what is called K-stable. Okay, and so there's a variation for extremal metrics, but I think it's easier if I just focus on the CSCK case. Essentially, most of the interesting things happen already at the CSCK level. So it just complicates the terminology to speak about extremal metrics. Of course, like in the toric case, there are definitely extra difficulties, but so let me just leave it as CSCK. And at this point, let me just give a kind of heuristic explanation of what this K-stability condition is. Instead of defining it precisely, the idea is that so if M does not admit such a metric, then what should happen? Then so the conjecture says that the obstruction is supposed to be what's called a test configuration. So, and that is a family. So and a test configuration is just a C-star equivariant family over C. The C-star acts on this whole family, and you also have to include the line bundle, but where the so the generic fiber is your M. The zero fiber is something possibly very singular. Maybe non-reduced. And the key thing that you do is, so this test configuration has the extra property that the induced from this C-star action, you get an induced action on M0, and this needs to have a certain numerical property. So this so-called Futaki invariant will be negative. Let me write it this way. So let me just call it the whole family. So this Futaki invariant of this, so a certain numerical invariant, which is a purely algebraic thing that you can compute from the rings associated to these projective varieties. And this should be negative, less than or equal to 0. And then, so later on, I'll say what this is precisely in the toric case. Okay, and then this YTD conjecture is known in several cases. So the very classical case is when L is the canonical bundle, or the canonical bundle is trivial. So this is the famous work of Yao. In this case, the stability condition is always automatically satisfied, and there's always a Kahler-Einstein metric. And then very recently, L is Km inverse. To Chen, Donaldson, and Sun. And then a little bit before that, like a few years before that, if M is a toric surface. And then in the CSCK case, this is due to Donaldson. And then with some mild extra assumption, the extremal case is due to Chen-Li-Sheng. And then I would say that pretty much every other case is pretty open. So the higher dimensional toric case is is very much open. Okay, so this is kind of a very brief introduction to extremal metrics. So I think everyone here has probably seen many talks on this already. But yeah, so the key problem is this existence question, that if you do not have a CSCK or extremal metric, then one needs to produce some sort of algebraic obstruction to this. Okay, so let me move on to the toric setting. So I'll give a very quick introduction to Kähler metrics on toric varieties. Okay, so now the additional assumption is that M has an effective torus action of an n-dimensional torus. So T action, and T is the real n-dimensional torus, and then so it's a holomorphic action. Let me just denote this complex torus by TC. Okay, and then what I want to study are T-invariant metrics on M. So let omega be a metric in the first term class of L, which is T-invariant. And then sort of the whole idea is to somehow reduce this problem. So Kähler metrics are always described by a scalar function on the manifold, and you want to reduce it from a complex n-dimensional manifold to just a real n-dimensional manifold using this T action. So what you can do is, well, this TC will live inside a manifold. So it's an open orbit. So there will always be this unique largest dimensional orbit. And then on this orbit, you can write omega as just, it will be dd bar exact. So you can write omega as I dd bar of some function, phi. Okay, so this phi is a Fourier subharmonic function on C star to the n. But then because of this T invariance, so this is T invariant. Because of the invariance, you can rewrite it as just a function of the moduli of the complex coordinates. So we can write this phi, so phi of z1 up to zn is really just a function, say f of log norm z1 up to log norm of zn. And then one can check that the condition for phi to define a Kähler metric, at least on this open set, is just that f is convex. So f will be a convex function from Rn to R. Okay, so this f is essentially the Kähler potential. Okay, and then what you do, so this is where we want to do this picture of changing the point of view to, instead of thinking about Kähler potentials, so a fixed complex structure, and changing the symplectic form, you want to transform to this other picture where you fix the symplectic form and vary the complex structure. And in this setting, that just amounts to taking the Legendre transform. So the gradient of f will define some map from Rn to Rn. And the image will be the interior of a polytope. interior of a convex polytope P. And it's just the moment polytope of this symplectic toric manifold. So the grad f can be identified with the moment map for the torus action. And then what I want to say is, so the symplectic potential is defined to be the Legendre transform of f, which will be some function on this image. So it's a u. Okay, so this is and typically both f and u are used, but in terms of u, this whole stability picture has a very nice description. Okay, so we need to just do a couple of things that, well, not any convex f will give you a metric that compactifies on the entire M, so there will be some boundary behavior at infinity that you require, which will then translate to some boundary conditions for u. And then the result of Guillemin is that this u, so near a face, let me write it like this, say L, say X. Let me write it like this. So suppose the interior of the polytope is defined. L is a linear, C, so L is linear. With integral coefficients, and you want a sort of primitive linear function. So AI will be in Z, and the GCD is 1. And you want the L to be positive, sorry, bigger than C. Okay, so anyway, each phase you can identify with such a linear function together with a constant. Then you normalize the linear functions in this way, and the metric has to have the asymptotics of the symplectic potential near this phase will be that it's like the linear function times the log of the linear function, and then plus something smooth. So let me just write it like this. Okay, so it's a kind of... Sorry, there should be a...
C should be 0.
Yeah, I guess I will. Yep, so in terms of like the real PDEs, that's a kind of interesting boundary condition. Okay, so the study of Kahler metrics on toric manifolds is basically equivalent to studying these convex functions with this boundary behavior on polytopes defined by these integral linear functions. And then you can compute the scalar curvature of this. And so this was done by Abru, and there's a very nice formula that the scalar curvature of the corresponding omega will be minus the sum over ij, and you have to take two derivatives of the inverse of the Hessian of u. Okay, so inverse of the Hessian of u. You take two derivatives and then like trace over the indices. So it's a fourth order operator. but it has a sort of very nice form. And so let me just give a very simple example. So e.g. on P1, so the CP1 corresponds, so if you have to pick a line bundle, so say with the O1 bundle, this corresponds to just the unit interval, so this moment polytope. So the corresponding polytope will be the unit interval. And then you can write down the Fubini's 2D metric in a simple way. So the ux will just be x log x plus 1 minus x log 1 minus x. And you can do this on any projective space of any dimension. And then the scalar curvature will be the minus, and you only have one variable, so the inverse Hessian is 1 over u double prime, and then you differentiate this twice more, and I think you should get 2. Okay, so it's this is a simple example of a toric Kahler metric. Okay, so this is the kind of differential geometric side of the picture, but so I need to tell you about the algebraic aspect. So what are the test configurations? So maybe I should just have said one more thing. So okay, so of course, scalar curvature, the CSCK condition is just that this function is a constant, and whereas the extremal condition is that this function is a linear, an affine linear function. So essentially, that's the PDE that we want to solve. And then the CRT and Donaldson conjecture says that if you cannot solve that, then you need to be able to cook up some kind of degeneration of the manifold to some possibly singular thing. Okay, so how do we describe these degenerations in the toric setting? Well, so suppose that we have this polarized toric variety with moment polytope P. Well, what you can do is consider a function, say f, which is a function that's convex and rational piecewise linear. Okay, so it's the maximum of a bunch of linear functions with rational coefficients.
Are the C's integral or the vertices of polytope?
So that doesn't need the C doesn't have to be. So that would.
This polytope doesn't necessarily have integral vertices.
Well, okay, I guess if in this case it should be integers, but the theory would make sense if the C's are not. It is important for these AIs. But yeah, let's assume the C's are also integers for simplicity. Like if they were not integers, you would just have a non-rational Kahler class, but still on a projective toric manifold. Okay, so if you have such a function, then what you can do is consider a polytope that has one larger dimension than P. So consider the polytope Q defined by the points, say, x, t, where x is in our polytope P, and the t is, say, bigger than or equal to the value of f at this x. So it's the stuff above the graph of f. Okay, so let me just draw a picture. So if this is our Rn, where the p lives, and this is this t variable, and you have some polytope, say p, then let me draw the function here. So you have some sort of rational, piecewise linear, convex function. You look at its graph, and then q is just everything above the graph. Well, this is also a convex polytope, and then by this correspondence between like toric varieties and polytopes, this also corresponds to a variety. And so it turns out that this q corresponds to, so it's not hard to show that q will correspond to some variety which has a C star action as well as a projection to C. And so it gives the total space of one of these test configurations. So you will have one of these pictures that I drew before. Okay, and then where the generic fiber will be our original manifold M, and let me just say, so the central fiber will generally be non-reduced. Sorry, I mean reducible, non-irreducible. Okay, and you can identify what the irreducible components are from the picture, so they will correspond precisely to these linear pieces of the function f.
So
the f is this convex rational piecewise linear function. And
I think it's a bit better, more rigorous to put polarization on that.
Yes, okay, that's true. I'm being a little bit sloppy. So there should be an L here, and then you might also need to tensor up things by a number. So you could assume after sort of scaling everything up that f has all integral coefficients, and then you'll have a line bundle on this too. So these polytopes correspond to polarized toric varieties. But what I wanted to do is just give an extremely simple example of this. Let me do it over here. So again, with P1, you can see very explicitly a very simple example. So for P1, with O1, so like I said, this moment polytope is just the unit interval. And then you can take the function, say, f of x, which is the max of half minus x and 0. Okay, so this is the function that looks like this. Okay, so it has these two linear pieces. And then through this correspondence, you can see that this corresponds to this, right? So f corresponds to the test configuration, which is just given by this family, xz minus t, y squared is 0. Okay, where t is the parameter in C, and then as t goes to 0. So the center fiber is this reducible like union of two lines, and that just corresponds to these two like linear pieces of the function f. And if so, yeah. I'm being a little bit sloppy that in this direction I want the projective variety, and in the vertical direction I just want to get to C. Yep. Yeah, so this is inside. Okay, and you can see that you sort of went up into, you get a degree 2 curve because you sort of have to scale things up to get rid of this half. Okay, so then this way we get a huge family of these test configurations just by picking any rational piecewise linear convex function. And then what you can do is compute their Futaki invariance. So Donaldson computed this, and the result is this nice formula that it's given by a linear function of these convex functions f, and of this form. So you have to integrate on the boundary of the polytope with respect to a suitable measure, and then there's a constant a. You integrate a times f on the interior. So a is going to be a constant, which is essentially the average scalar curvature. So this will be determined by the condition that L of 1 is 0, and that d sigma and d mu are just sort of natural measures that you can define on the boundary. Well, and d mu is just a Euler-Lagrange measure on P. And I can just make a remark that for extremal metrics, so this will be the relevant Futaki invariant when you're looking for constant scalar curvature metrics equal to a. Well, if you're interested in extremal metrics, then you just replace this a with the corresponding linear function. And then again, the very first necessary condition to be able to find a metric with the scalar curvature is that this L of is 0 for all affine linear f. Okay, so in terms of all of this, this Yati and Donaldson conjecture for toric manifolds says that you can find a constant scalar curvature metric. So M admits a CSCK metric in this scalar class. If and only if it's k-stable, and in this case, k-stability. So the conjecture is that it's enough to check the test configurations that you obtain from this construction. So if and only if this So Tachy invariant is non-negative for all piecewise linear convex rational f, and with equality only for affine linear f, for all rational piecewise linear convex f, and it can only equal 0 if f is affine linear.
So are you using uniqueness of extremal metrics to know that if you have one, it has to be of this type, it has to be invariant into this triple?
Yeah. So in fact, that's an easier result. So that's already due to Calabi, that an extremal metric is always invariant under a maximal compact subgroup. But it's not obvious that it should be enough to check these toric test configurations. That, I mean, in principle, even if the original Yati and Donaldson conjecture were known, I mean, this would still not follow that it's enough to check these sort of torus invariant test configurations. But I mean,
so you would
if one,
if it exists, is invariant, but that doesn't mean the test configuration is.
I mean, presumably, if one could prove the big conjecture, then one could also prove this. Yeah, all I'm saying is that it's not an immediate consequence. So a priori, I mean, there could also be a lot of other test configurations with like non-reduced central fibers or some. I mean, these have kind of pretty mild singularities. That is just it's just the union of. I guess they could be singular, but these central fibers are pretty nice. But you could, in principle, have much worse things. And so part of the conjecture is that it's enough to check these nice test configurations. Okay, so maybe in the last 10 minutes, let me just talk about some existence results that are known. So,
maybe I didn't quite follow. Are you saying that one can prove that the Yati and Donaldson does reduce to this statement in the toric case, or is this a refinement in the toric case of the conjecture?
I think if one could prove the general conjecture, then probably the same techniques would also prove that it's enough to check this. But I don't know, because I don't know the proof of the general. But all I'm saying is that it does not formally follow, but presumably it's not a. Well, one could just try doing everything equivariantly, and then it would reduce to this. Although I suppose part of the question would be, and I mean, this is actually I think an important question, whether even if everything is torus invariant, whether these, I mean, the way the metrics degenerate, that you could expect to see more complicated f's which are not piecewise linear, or even if they're piecewise linear, they might not be rational. Okay, so I'll come to that in a second. Okay, but so this is the toric version of the Yati and Donaldson conjecture, as it's sort of usually stated. Okay, so what do we know about existence? Well, the first results were due to Wang and Zhu in sort of 2006, maybe, or earlier, maybe early 2000. So if we're in the Fano case, so if L is the anti-canonical bundle, then it's enough to check just this last condition. So, Okay, so in terms of the heuristics, that the point would be that if M does not admit a Kahler-Einstein metric, then there should be something happening as you try to find such a metric. Well, this is somehow saying that if there does not exist a Kahler-Einstein metric, then you only need to worry about the generations, which are actually just sort of product configurations. They come from the vector fields on the toric manifold. So we only need to look at, so let me state it this way, we only need to consider test configurations with the central fiber being the same as M. So the total space will be M cross C, just with a non-trivial C star action. And in fact, what happens is that if M does not admit a Kahler-Einstein metric, well then, in fact, it admits a Kahler-Ricci soliton, and somehow that's the obstruction to admitting a Kahler-Einstein metric. Okay, so then Donaldson has a series of papers on the case of toric surfaces, and the upshot is that the conjecture as stated here is true. Just to emphasize, so this applies to CSCK metrics. And let me just say something about the ingredients. So, and of course, this will be extremely brief, but one thing that I want to emphasize is that there's a sort of very non-trivial sort of first step to get something slightly better out of the stability condition. So one key result is that if you have the strict positivity for all non-affine linear, like rational piecewise linear convex F, then actually you have a sort of uniform version of this result. So then there exists some delta such that you have the following inequality. You'll have LF is bigger than or equal to delta times the integral on the boundary for all convex functions where you have to normalize them suitably. So now this holds for all convex F with, say, F of 0 equals 0 and F non-negative. And 0 is just a fixed base point inside P. That you just fix once and for all. So the point is that, so you can always, so it's easy to show that if under this assumption that LF is bigger than 0, LF will be 0 for all affine linear F. So then you can always normalize any F to satisfy these conditions, and then only worry about these convex F. But then the point is that you get this sort of uniform positivity in terms of this norm. Okay, so then maybe I should call this. So this condition is often called uniform stability. Well, okay, so given this, it is from this and the sort of simple integration by parts argument, you get a very easy first a priori estimate. Oh, sorry, I meant interior. Okay, so if you have a constant scalar curvature metric and you have this uniform stability condition, and you can normalize this U since it only involves the Hessian, this equation. So then it's pretty easy from this to show that you have an a priori estimate for this integral. Okay, and in particular, you'll get interior, say, at least first derivative bounds or like a Lipschitz bound from just the convexity, and then sort of much more work using sort of pure PD techniques and also other geometric arguments. You also have higher order derivatives. So the soup on, let me just write it like this. So for any relatively compact subset, you'll have these estimates. So this uses sort of more established techniques from affine geometry too. So it uses like techniques of Caffarelli, Gutierrez. It's essentially, you can do it in a sort of pure PDE way. But what seems to involve a lot more like geometric arguments is to get estimates on the boundary. So like we've also seen in the previous talk. So then you need boundary estimates. So okay, and let me not say anything about this. So this is the surface case for CSCK metrics. And then finally, the most recent results is the work of Chen-Li-Sheng. So this is an extension of this result to extremal metrics. So still dimension is 2. And we obtain the existence of extremal metrics. However, this first step, as far as I know, seems to be like missing. So it seems to be, in some sense, this is the most elementary part of the whole argument, but it really seems to use the constant scalar curvature condition. So in the extremal case, in fact, this is the assumption that we have this uniform stability condition. Maybe just let me mention one final result. So it's the work of Chen. So this seems to be one of the few higher dimensional results. So Chen, Han, Li, Sheng. They showed interior estimates. So the same estimates as over there. In the higher dimensional case, but only if there's an extra assumption. So in terms of a global, so in terms of a global sup bound on U, then you can get interior derivative estimates on the interior. Oh, you've already removed that?
Yeah. So in the early paper, without Han,
we need a C0 estimate, but with the hand we don't need it. We get the integral estimate.
Oh, I see, with no assumption. Oh, okay, good. That's an even more recent result. But so is that with Han or without Han? Yeah. It's still. Oh, I see. Okay.
Without Han, we have the one with the assumption.
Oh, I see. Okay. And but it's so assuming uniform stability.
Yeah. Yes.
Uniform stability is the sense.
So it's this. So this is the. So this assumption that there is a delta such that this estimate holds for all convex F. And so what seems likely is that in this extremal case on surfaces, but also in higher dimensions for CSCK metrics, it seems pretty likely that, in fact, this conjecture, as stated here, is not true, but you have to assume something stronger. And this is similar to these examples of Apostolov and collaborators, where there seem to be some ruled surfaces which do not admit extremal metrics, but we're pretty sure that they're stable. Although we can't prove it, but it seems almost certain that they are stable, but they do not admit extremal metrics, and one needs some kind of refinement of the stability notion, like something which will give this uniform condition. And this should be related to, how, when you're trying to find extremal metrics through some continuity method, then what seems likely is that the possible degenerations are not necessarily algebraic, but you have some kind of more complicated situations, which will lead to, some non-rational piecewise linear F, which will obstruct this condition. All right, I think I'll stop here.
Questions? So you expect this, so you actually expecting uniform stability is in fact stronger than stability?
I think it seems likely.
Okay. It's stated because it's stronger, but you're saying that actually there will be examples for stability, but not uniform stability.
I think that there should be. And so in this two-dimensional case and toric surfaces, at some point you have to use that a quadratic polynomial with integer coefficients. If it has a double root, then that root is rational.
I see.
So then when in higher dimensions you'll have higher degree things, which is also the source of these examples of Apostolov.
I see. So
it's really the rational. If we change the conjecture by rubbing out rational, then.
But maybe even you have to
erase more. That would be more.
This much. So my guess is that we want to erase these.
Prove that.
But maybe. But I do think it seems to depend on the geometry of how the things can break. And
but if for uniform stability with piecewise linear, you think it's okay?
Well, but so then you can just approximate, you can take limits and then.
In all dimensions, uniform stability, it's okay.
Uniform
stability with piecewise linear rational function, it's okay.
Oh, sure, yeah.
That's okay. I see. So what about in the final case? Is uniform stability equivalent to stability?
Yeah, I think that's known by Darvan and other people.
No, just algebraically.
Oh, algebraically, but so in the Fano case, you can check, but in the toric case, or in the toric case, you can directly prove uniform stability whenever the Futaki invariant vanishes.
So you
just sort of, it is just a sort of integration in polar coordinates on these polytopes.
I see. Okay.
May I make a remark that we also have the result that uniform stability is the necessary condition.
Sorry. Yeah, so that.
So that's already the necessary condition.
Yeah.
you say that again?
Yeah, so the uniform stability, it's known that uniform stability is necessary for the existence of extremal metrics. So yeah, that would give that and only if in that surface case.
So uniform stability sounds true. Surface case.
And in all dimensions, uniform stability is necessary for the existence. But this is also in your paper, right?
Yeah. So that's why we're assuming the uniform stability at the moment.
Yeah.
Let's thank Gabor again.